If you ever square root a number and it doesn't neatly turn into a whole number or a simple fraction, then you've just found a surd. At first glance they might seem intimidating, but surds are actually a fascinating and vitally important topic in maths. By the end of this video, you won't just understand surds, you'll know everything you need to use them for GCSE and IGCSE maths and for maths challenges. In part 1, we'll cover the fundamental rules of multiplying, dividing and simplifying surds. Then in part 2, I'll show you how to use the algebra you already know to multiply surd expressions easily. Part 3 is about rationalising denominators in the simpler cases, and then we'll break down the difference of two squares formula in part 4, which is essential for the most advanced techniques in part 5, where we will tackle rationalising denominators in tougher cases. Mathematics is about understanding both the why and the how, not just getting the right answers, and my teaching approach is about transforming maths from just another subject into a valuable skill and an enjoyable part of your life. So whether you're navigating through GCSEs and A-levels or preparing for maths challenges and Olympiads, you can find lots more at courses.mathsaurus.com, and many of the courses there are totally free as well. So back to this video, if you stick with me until the end, I'm sure you'll start seeing surds in a whole new light, so let's get started now. When I talk about surd expressions, I'm really talking about things that have square roots in them, okay? We might also talk about questions with cube roots and higher roots, but for now, we'll just look at square roots, okay? And the main result we're going to use to begin with is that the square root of a times b is equal to the square root of a times the square root of b. So that means if I've got an expression like the square root of 50, I can write it as the square root of 5 times the square root of 10, because 5 times 10 is 50. Or even more usefully, I might be able to write it as the square root of 2 times the square root of 25. That can be useful because the square root of 25 is 5, a whole number, so I could say that that's just 5 times the square root of 2. Okay. So we're going to do a few examples like this in a second. But in principle, you're allowed to split the surds up however you like here. So why is this result true? Okay, so what do we actually mean by a square root, right? A square root is a number that when you multiply it by itself gives the number you're looking for, right? So the square root of a satisfies the property that the square root of a times the square root of a is equal to a. That is the definition of the square root. And similarly, the square root of b times the square root of b is equal to b. Right? So to show that this is true, this first result here I mean, what I'm going to do is just multiply the square root of a times the square root of b by itself. Okay, the square root of a times the square root of b times the square root of a times the square root of b. Now, we know we can do multiplication in any order we like. So I could, rather than multiplying it in this order, I could do the square root of a times the square root of a times the square root of b times the square root of b, just reordering these four things that I'm multiplying together. 2 times 3 times 4 times 5 is the same as 5 times 3 times 4 times 2. So now, by the definition of the square root of a, this first one is equal to a, root a times root a is a, and then root b times root b is equal to b. Okay, so I've got that when I multiply this number, root a, root b, by itself, I get a times b. Now that is exactly the definition of the square root, right? It's a number that when I multiply it by itself gives that thing. So it must be that the square root of a times b is equal to the square root of a times the square root of b. So as we saw in that first example where we wrote the square root of 50 is equal to the square root of 2 times the square root of 25, this result is particularly useful when one of the things that we factorise is itself a square number, because I can then simplify the surd expression down. Okay, so if I've got something like the square root of 8, I could possibly simplify that surd if I can factorise 8 in such a way that one of the numbers is a square number. So here 8 is 4 times 2, 4 is 2 squared, so the square root of 4 is just the number 2, and that means that the square root of 8 is 2 times the square root of 2. And this is now a surd in its simplified form. Okay, so we should always, when we have surd answers, look to simplify them if we can. A bit like we'd always cancel fractions down. If we get an answer that has a surd expression, we're going to try and leave it in its simplified form. Another example, I could do the square root of 45. I'm looking for the largest square number that I can pull out of this as a factor. So I can do the square root of 5 times the square root of 9 here. 9 times 5 is 45. The square root of 9 is just 3, so this gives me 3 times root 5. This can be very useful because if I've got something like the square root of 72 plus the square root of 200, and I do this for both of the expressions, right, like so 72 is equal to the square root of 2 times the square root of 36, and the square root of 200 is the square root of 2 times the square root of 100, then I can write this as 6 root 2 plus 10 root 2, and add those together and get 16 root 2. It's going to be lots more like this to practice on in the examples, but these two numbers, root 72 and root 200, don't obviously look like they combine in a nice way, but in fact, once we've simplified them, they do combine in a very nice way, like this. The final step here, we do just like algebra, right? So if it's 6x plus 10x, I get 16x, and we're just using this result here where, in this case, x is equal to the square root of 2. So you can sometimes simplify surds and then need to simplify them further, right? So like 72 here, I could also have done the square root of 72 is the square root of 8 times the square root of 9, and got that that's 3 root 8. Now that wouldn't have been as good an answer as 6 root 2 because it's not fully simplified, and I wouldn't then have been able to combine these terms. But root 8, you see, we've already seen as 2 root 2 because it's root 4 root 2. So this would be 3 times root 4 root 2. So that gives me 3 times 2 times root 2, which again is 6 root 2, just as we found before, of course. One other consequence of this multiplication result here is that there's an equivalent one for division. So if I have the square root of a divided by b, for exactly the same sort of reason, I can write this as the square root of a divided by the square root of b as well. So sometimes we might use this to do some simplifications as well. For example, if I had something like the square root of 27 over the square root of 3, I could just say, that's the square root of 27 over 3, which is the square root of 9, which is equal to 3. All right. Alternatively, I could write that the square root of 27 is the square root of 9 times the square root of 3, so it's 3 root 3, and so I can get the same result using the multiplication rule instead. I could say the square root of 27 over the square root of 3 is 3 root 3 over root 3, and then I can cancel the root 3's top and bottom as well. So different ways of doing it, but this division rule is really an extension of the multiplication rule that we can use when we need it as well. So this comparison with algebra is an idea that I think I've always found students find helpful if they find these surds at all difficult. So if I want to multiply out something like 3 plus root 2 all squared, I'm going to think of it just like multiplying out 3 plus x all squared, but x is equal to the square root of 2. So it has the property that when I square it, x squared is root 2 squared, which is 2. Okay. So if I were to multiply out 3 plus x all squared, we remember it has to be 3 plus x times 3 plus x. Maybe you've remembered the standard form for this by now, or if not, we can just multiply it out term by term. 3 by 3 is 9, plus 3x gives us 6x, and then I get plus x squared. Now in the surds case, I've got something very similar then. It's going to be 3 plus root 2 times 3 plus root 2. So I'm going to get 9 plus 6 times root 2, right? It's 3 times root 2 plus 3 times root 2, and then I'm going to get root 2 squared. And the extra thing we do for the surds case is we remember that root 2 squared is 2. So this is 9 plus 6 root 2 plus 2, and that gives me 11 plus 6 root 2. So we can do this for other expressions. If I want to do 3 minus root 2 times 5 plus root 2, again, I'm going to multiply it out just like I've got 3 minus x times 5 plus x. Okay, so in this case it would be 15 minus 5x plus 3x minus x squared. That would give me 15 minus 2x minus x squared. And in this case I'm going to do 3 times 5 is 15. I've got minus 5 root 2 plus 3 root 2, and then minus root 2 squared. Now you don't have to write this root 2 squared every time. Perhaps if it was a show that question, you might do it. But I'm happy to jump to root 2 squared being 2. So 15 minus 5 root 2 plus 3 root 2. Again, that's just minus 2 root 2, just like we get minus 2x here. And then minus root 2 squared gives us minus 2. So here I get 13 minus 2 root 2 as my final answer then. So one thing to notice is that if you multiply out something like 3 plus root 2 times 5 minus root 3, that you are not going to be able to do so much simplifying, right? This is more like multiplying out 3 plus x times 5 minus y, when the surds are not the same. if I multiply this out, I'd get 15 plus 5x minus 3y minus x times y. And the same here, right? I'm going to get 3 times 5 is 15. I'll have plus 5 root 2 minus 3 root 3. And then I've got minus root 2 root 3. And in this case, we would usually use that rule, root a times b is equal to root a root b, the other way around, and write this as a single surd, root 6. But do watch out, sometimes when they look different, if they're unsimplified, they might actually have something in common. So if I did 2 plus root 8 multiplied by 3 minus root 2, well, we've seen already that root 8 is equal to root 4 times root 2, which is 2 root 2. So I can actually write this as 2 plus 2 root 2 times 3 minus root 2. And now multiplying it out, I will get more combinations. So 2 times 3 is 6, 2 root 2 times 3 is 6 root 2, then I'm going to have a minus 2 root 2, and then finally I'm going to have a minus 2 root 2 times root 2. Root 2 times root 2 is 2, so that's 2 times 2, which is 4. So I've got 6 minus 4 is 2, 6 root 2 minus 2 root 2 is 4 root 2. Rationalising the denominator where it's just 1 over the square root of a number, what we do is we multiply top and bottom by the denominator here. So I say 1 over root 3 is the same as 1 over root 3 effectively times root 3 over root 3. Okay, so that's root 3 over root 3 times root 3, and root 3 times root 3 is 3. Okay, so that's root 3 over 3. By the way, I wouldn't usually write out all these steps. I'm just doing that to try and explain what's going on here. It'd be totally fine here just to go straight to the final answer if you can do that. And having a rational denominator is a lot simpler because dividing by surd expressions is very awkward, whereas just dividing a number by 3 is not so bad at all. If you might even think about doing this just like with a long division or something, right? If I just go to the calculator here and work out what the square root of 3 is, for example, let's just do it to a few decimal places. Right, I get 1.73205. Okay. Right, if I try to do 1 divided by this, right, and try and do this as a division, like that is really something quite messy to do. But if I do the square root of 3 divided by 3, well, I'm just doing 3's into 1.73205. So to get this to like 4 or 5 decimal places or something, all I need to know is root 3 to that number of decimal places and then just divide it by 3. Now, obviously I still need to know what root 3 here is for this to work, but I need that either way. And this is particularly important when say computers do arithmetic, right? So actually a computer is going to find it much easier to calculate this in this form compared to in this form. So there are lots of implications in these kind of examples for how we might, how computers might do things efficiently. But it's also just kind of our instincts for why this sort of expression is a lot simpler. So we want to avoid having surds in the denominator where possible. So if I've got, for example, 2 over the square root of 7, I'm going to just multiply top and bottom by root 7, get 2 root 7 over root 7, and that gives me 2 root 7 over 7. And this is a much simpler form than this one, even though it's got 3 things in it rather than 2. This is just 2/7 of the square root of 7, so it just involves multiplying by root 7, unlike this expression, which requires dividing by it, which is just really a lot worse. Okay, so just a few examples there. Hopefully you've seen this before. I suppose we could also have one where I've got a surd on the top as well. I could do something like root 3 over root 6. Here I've got a couple of choices. I could just multiply top and bottom by root 6 here and get root 6 times root 3 over 6. But in this case, I'm going to end up with root 18 over 6. And on the top then I've got to simplify that. That's root 9 root 2 over 6. Remember, I should always simplify surds if I can. And that's 3 root 2 over 6. And now I cancel off 3 top and bottom, and I get root 2 over 2. Now I could have done this so much more efficiently if I just noticed there was a factor of 3 in common top and bottom here, and used the fact that the square root of a, over b is the square root of a over the square root of b effectively, to say that this is the same as the square root of 3/6, so it's the same as the square root of 1/2. So I'm effectively, or you could think of it as writing this as root 3 over root 3 root 2 and cancelling a root 3, so I've just got 1 over root 2, and then I can multiply top and bottom by root 2 to rationalise and get root 2 over root 2 root 2, which is root 2 over 2. Okay. So I get the same answer either way. It's nothing wrong with doing it either way here, but we're always looking for the most efficient. So the second case of rationalising surds is all based on the difference of two squares formula that you will have seen at GCSE, and we're going to use it over and over again at A level. So we're going to recap it here, and we're going to look at some more complicated examples of it where we've got surd expressions involved. Okay, so what does the difference of two squares say? Well, it just says if I multiply out a plus b times a minus b, right, I get a squared, I get a plus ab, I get a minus ab, and then I get minus b squared. So actually I get here a squared minus b squared, right? So we often use this to do a bit of calculation quickly. If I want to do something like 101 times 99, I could think of it as 100 plus 1 times 100 minus 1, and that would give me 100 squared minus 1 squared, so that's 10,000 minus 1, so that would just give me 9999. I mean, you could also do that calculation pretty quickly directly by just saying it's 100 times 99 plus 1 times 99, but you could apply the same logic here and do 108 times 92, right, and do 100 plus 8 times 100 minus 8. So that again, by the difference of 2 squared, is 100 squared minus 8 squared, so that's 10,000 minus 64, which gives us 9,936. But the main purpose of this isn't just to come up with like neat calculation strategies, fun as these are, and these are good for maths challenges and things like that. But we're going to be looking at evaluating them with surd expressions in them. Okay, so if I had something like 6 plus the square root of 3 multiplied by 6 minus the square root of 3, then I could think of this as the difference of two squares. I can say, well, this is just 6 squared minus root 3 squared, so this would give me 36, and then minus root 3 squared, so that's just minus 3, and that's 33. And the fact that this is always going to give you a whole number is really helpful, right? So if I have the square root of 7 plus the square root of 5, say, and I multiply it by the square root of 7 minus the square root of 5, in themselves, not very nice numbers, these two things that I'm multiplying together, but the difference of two squares formula is going to say, that's the square root of 7 squared minus the square root of 5 squared, so that's just 7 minus 5, which is equal to 2. And we're also going to want to apply this with some slightly more complicated examples. So maybe I'll have something like 2 times the square root of 5 minus 3 times the square root of 7, and if I multiply that by 2 root 5 plus 3 root 7, again the difference of two squares formula is going to tell me this is 2 root 5 squared minus 3 root 7 squared, so 2 root 5 squared, be very careful here, this is going to be 2 times root 5 times root 5, so it's 2 times 2 is 4, times root 5 squared is 5, and then minus 3 squared here is 9 times root 7 squared, which is 7, so that's going to give me 20 minus 63, and that gives me minus 43 here. So again, a whole number. So we're going to be using this difference of two squares expansion to rationalize some more surd expressions, including some quite tricky ones. Why does this difference of two squares expression help us so much in rationalizing surds? Well, it helps us deal with this case where we've got something a bit more complicated in the denominator. So if I wanted to do something like 7 divided by 2 plus root 5, and I want to try and rewrite this without there being any surds in the denominator, the problem with applying the previous method, where I just multiply top and bottom by the surd, root 5 here, right, is that I don't end up with a nice denominator, right? I get 2 root 5 plus 5, so it still has the surd in the denominator. But I can get things that are not surds by forming difference of two squares expressions, right? So I know that 2 plus root 5 times 2 minus root 5 is going to be a whole number. And I can keep the fraction the same by just making sure I multiply top and bottom by the same number, right? So I've multiplied the denominator by 2 minus root 5. If I multiply the numerator by 2 minus root 5, I haven't changed that fraction, okay? So if I was to write out slightly fuller working here, I might say that this is equal to 7 times 2 minus root 5 over 2 plus root 5 times 2 minus root 5. And now you see, let's just leave the top as it is. On the bottom, I've got a difference of two squares, right? So I've got a plus b times a minus b. So that's just a squared minus b squared. So that's 2 squared, which is 4, minus root 5 squared, which is 5. And so I've just got minus 1 on the bottom here, right? So I've got 7 times 2 minus root 5 over minus 1. And now for a simplified form, we should never leave a negative number in the denominator. So I can write this as, well, I could write minus 7 times 2 minus root 5, but it's neater here just to write that as root 5 minus 2 by multiplying this whole bracket by minus 1, and then it would be over 1, so I don't need to write that, and that's the answer there. Okay, so let's look at another one. If I had the square root of 5 here on the top, and on the bottom, let's say we've got 3 minus the square root of 6. So to make a difference of two squares expression, this time I need to multiply by 3 plus root 6. Okay, and if I multiply by top and bottom the same, if I multiply the top and the bottom of the fraction by the same thing, we end up with a fraction that is equivalent, a number that's equivalent to the one we started with. Right. So the takeaway here is that what do? We look at the whatever is on the bottom of the fraction, and we try and form this expression. I often call this a conjugate type expression. This language comes from a different part of maths, but it's basically when I've got something like this and I want to have a word to describe what is the kind of equivalent expression, but I've replaced the plus with a minus, or in the second example here, I've replaced the minus with a plus. Okay, so you know, this one I started with root 5 over 3 minus root 6. So again, I look at this minus and say, to make a difference of two squares expression, I want the same sort of thing, but I want a plus instead of a minus. And that's what I multiply top and bottom by. Right. So by doing that, I've got on the top here 3 root 5 plus root 30. And on the bottom, I've got 3 squared is 9 minus root 6 squared, which is 6. So I end up here with 3 root 5 plus root 30 divided by 3. Looks like there should be a factor of 3 top and bottom here or something, but it's not quite because the 30 is inside the square root there. So we have to leave it just like that. Another example here, I've got 2 over root 11 minus root 7, and the same sort of idea can work here, right? If I just look at the denominator and change the minus to a plus and multiply by that expression, right? So root 11 plus root 7 instead of root 11 minus root 7, we've seen this sort of thing gives us a difference of two squares. So on the top I've got 2 times root 11 plus root 7. Again, I'm not going to multiply that out here because I've got a whole number factorized out. And then on the bottom I've got root 11 squared minus root 7 squared. Okay, so that would just be 11 minus 7, again using the difference of two squares. And 11 minus 7 here is 4. So actually, I can also cancel down a factor of 2 here and just leave this as root 11 plus root 7, all divided by 2. There's another example, 2 plus root 3 over 3 root 5 plus 4. Again, let's form that conjugate expression to get the difference of two squares. On the bottom, we've got 3 root 5 plus 4 here, and I'll multiply that by 3 root 5 minus 4. Change the plus to a minus and multiply by that. I've multiplied the numerator by this, so to keep this the same, I'll have to also multiply the denominator by the same number. And here I've just got something a bit more complicated. I'm going to multiply out the top here and get 2 times 3 root 5 is 6 root 5. and then minus 2 times minus 4, so minus 8. I've got plus 3 times root 3 times root 5, so that's plus 3 root 15. And then I've got minus 4 times root 3. Now notice when you've got different surds, we don't get much simplification here. So you could argue in some situations you might be better not to multiply at the top and leave it as it is. But we'll do that here. And on the bottom I've got the difference of two squares. So I've got to do 3 root 5 squared minus 4 squared. Right. So now 3 root 5 squared is just 3 root 5 times 3 root 5, so that's 3 squared times root 5 squared, so that's 9 times 5, which is 45. So on the bottom here I've got 45 minus 16, which is 29. And on the top, it doesn't really matter what order you leave these in, although some people would say put the whole number first and then put the surds in order if we're going to agree on a way to write these down. So just in numerical order increasing here, but whichever way you write this expression down is fine as long as it's equivalent to this.